How can fluid mechanics explain how a plane stays up in the air? One of the fundamental equations of fluid mechanics is Bernoulli's equation. Bernoulli's equation has been used to describe how an airplane wing generates lift. There are other ways to describe the phenomenon of lift, and there are arguments for and against each one of them. In this lesson, we'll try to make sense of the Bernoulli equation's application to flight. Let's start with some things we know about a plane traveling through the air. There are four significant forces acting on the plane: thrust, drag, weight, and lift. Thrust is produced by the plane's engines, and drag is the resistance the plane experiences as it pushes through the air. Weight is the effect of gravity pulling on the plane's mass. So that just leaves lift for us to explain. Lift comes from the difference in pressure above the wing and below the wing. When the plane is at rest, the pressure above and below the wing is the same. However, when the plane is traveling through air, the pressure above the wing is lower than the pressure below the wing. This pressure difference creates a net force perpendicular to the wing called lift, which pushes up on the plane. How does fluid mechanics help explain the lift force acting on the plane? Well, for one thing, the air that the plane is flying through behaves like a flowing liquid. That's why we can apply the Bernoulli equation to it. Bernoulli's equation is written like this: P plus 1/2 rho V squared plus rho GH equals a constant. In this equation, P stands for pressure at any given point in a flow. Rho stands for the density of the fluid at that point. The V stands for the velocity of the flow at that point. G stands for the acceleration due to gravity. And H is elevation of the point in the flow. What does the equation mean? Simply stated, the Bernoulli equation gives us the following principle. When the velocity of a fluid increases, the fluid pressure will decrease. To understand how this equation applies to flight, we want to compare 2 points within the flow of air in which a plane is flying. Point 1 will be on the top side of the wing, and point 2 will be on the bottom side of the wing directly beneath point 1. This is how the Bernoulli equation would describe it. P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Let's start to simplify this equation. Since the plane is traveling horizontally, H is the same for the 2 points we're comparing, and the density of the air is constant. Therefore, rho GH1 equals rho GH2, and the formula can be simplified to P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. We can see from this simplified form of the Bernoulli equation that if the velocity of the airflow is greater above the wing than it is below the wing, that the pressure above the wing will be smaller than the pressure below the wing. But aren't the top and the bottom parts of the wing moving at the same velocity? Yes, relative to the ground they are, but because of the design of the wing, the velocity of the airflow over the top and bottom of the wing are not the same. Relative to the wing, the air moves faster above the wing than it does below the wing. Explaining wing design and how that works is another lesson. Okay, this leaves us a big question. What causes the pressure to decrease just because the velocity has increased? To understand why the pressure decreases, it's helpful to think about what causes pressure. Pressure is caused by the change in momentum of molecules of a gas. Molecules of a gas are always moving, and when they collide with the surface, they bounce off, imparting a small force. Pressure is the sum of these forces per given area. So imagine a quantity of gas, let's say 1 gram of air, occupying a cube of space. If that cube were to sit on a stationary surface, The collisions of the molecules hitting that surface would create pressure within the area of a square. Now think of that gram of air moving at some velocity over the surface of a wing. The collisions of the molecules from that 1 gram of air would be spread out over an area shaped like a rectangle instead of a square, stretched in the direction of the motion. There would be fewer collisions in any given area because of this motion. The number of molecules in the 1 gram of air that passed over the wing would not decrease, but the pressure pressing down on the wing would decrease because the gram of air was part of a flow rather than stationary. Now, if a similar gram of air is flowing across the bottom of the wing more slowly than the molecules flowing across the top, then the molecules flowing across the bottom will be bouncing off the surface of the wing, exerting more force per given area. The net result would be a greater pressure under the wing than above the wing. And that, ladies and gentlemen, is the lift that keeps a plane in the air.